Hello. This podcast is on kinematics and Newton's second law. Remember, kinematics is just the term for the study of motion. First, we're going to take a look at relating forces to motion. Then we're going to quantitatively analyze how forces cause motion. We're also going to quantitatively predict forces from an object's motion. And finally, at the very end of this podcast is a review of the kinematic equations from an earlier unit. First, let's talk about how we relate forces to motion. Newton's second law relates force quantities to each other. The three kinematic equations relate the five motion quantities to each other. So let's take a look at these. First, the force quantities. We have net force, mass, and acceleration. And over on the motion side, the five quantities are initial velocity, final velocity, displacement, elapsed time, and acceleration. We have math equations for both forces and motion. The math equation for forces is Newton's second law. The net force is equal to mass times acceleration. And for motion, we have the three kinematic equations shown here. Notice between the force side and the motion side, acceleration is the connecting bridge. And we're going to use that in our problem-solving process. So let's move on and take a look at a problem-solving strategy. There's actually two types of problems we're going to be looking at, so we need to develop two problem-solving strategies. So the first one I call forces cause motion. Here the problem gives you all the information you need to know about the forces, and it asks you to calculate one of the five motion quantities. Here's the first step. Draw a quantitative force diagram. Next, use Newton's second law to write the force equation for the dimension of the motion. And of course, that dimension is either along the x-axis, which we often call horizontal, or along the y-axis, which we can also call vertical. Once you've written the force equation, you want to rearrange it to solve for acceleration. Then, once you have acceleration, go back to the word problem and list all the motion quantities you're given in the problem. Next, pick one of the kinematic equations. It has to have acceleration, the quantity you need to calculate, and the two quantities you know from reading the problem. If the equation isn't set up to solve for the unknown quantity, you'll need to rearrange it so you can solve for that unknown quantity, and finally calculate the answer. Let's put this strategy in practice. We have a 1,000-kilogram car traveling at 25 meters per second. Its brakes can apply a 5,000 Newton force. What is the minimum distance required for the car to stop? So they've given us the force information and they're asking us to find the minimum stopping distance. Well, that's just another term for displacement. So this is the first type of problem. We know about the forces and we need to find out something about the motion. First, let's draw a force diagram. So in this case, I'm having the car go to the right. There are no forces acting to the right, but then when the person applies the brakes, that creates a friction force to the left, slowing the car down. And of course, our gravity force and normal force balance each other. And we calculated those forces from the 1,000-kilogram mass of the car. Next, we need to use Newton's second law to find acceleration. So I go ahead and rearrange the equation, and that's acceleration equals net force divided by the mass. So the net force of the brakes is 5,000 newtons, and since I'm having the brake force act to the left, I put a negative sign in front of it. We divide that by the mass, and we have a acceleration of -5 newtons per kilogram, or keep in mind newtons per kilogram is the same as meters per second squared. So next I need to make a list of the quantities that I have in the problem. Well, I'm told the initial velocity is 25 meters per second. I know that when the car comes to a stop, the final velocity will be 0 meters per second, and I need to find the displacement. So the equation I need to use is equation number 3, and I'm going to rearrange it to find delta x. And so that's the final velocity squared minus the initial velocity squared divided by 2 times the acceleration. And I go ahead and plug in my velocity information, which I got from the problem. And I also plug in my acceleration, which I got from Newton's second law. And I find out that it took the car 62.5 meters to stop. This is about 70 yards. Let's look at our second type of problem. I call this predicting forces from motion. In this problem, you're given three motion quantities and you're asked to calculate a force. So here's the strategy for this. First, list all motion quantities given in the problem. Next, pick one of the kinematic equations that has acceleration and the three quantities you know from the problem. Next, rearrange the equation to solve for acceleration. Once you have acceleration, draw a quantitative force diagram and fill in all the forces you know. Then, use Newton's second law to write the force equation for the dimension of the motion. Again, that's either the x or horizontal dimension or the y, also known as the vertical dimension. Next, rearrange the force equation to solve for the unknown force. And finally, calculate the answer. Let's put this strategy to practice. A race car has a mass of 710 kilograms. It starts from rest and travels 40 meters in 3 seconds. The car is uniformly accelerated during the entire time. How big is the net force acting on the car? Well, as we read the problem, we see that they've given us some information about the motion quantities. We have displacement, initial velocity, and elapsed time. And they're asking us to find a force, in this case the net force. So this clearly falls into predicting force using motion. So first we want to look at the quantities we know, the kinematic or motion quantities. We know the initial velocity is 0 because it starts from rest. Displacement is 40 meters and elapsed time is 3 seconds. So we need to find the kinematic equation that has these three quantities plus acceleration. Well, that happens to be motion equation 2. I go ahead and rearrange it to solve for acceleration. And we have that it's equal to 2 times the displacement divided by delta t squared. We go ahead and plug in our information from the problem. And we find out that this car is accelerating at 8.9 meters per second squared. Next, I want to draw a force diagram. Our vertical forces are the force of gravity and the normal force of the road, and they're balanced. There is no motion vertically. Of course, the acceleration is happening horizontally or along the x-axis. I have a traction force to the right, the road pushing the car forward, and to the left I have a frictional force, drag force between the road, the air, and the car. So those are my forces. Now I need to go ahead and use Newton's second law to find the net force. And the net force is equal to the mass times the acceleration. So I plug in my mass, I plug in my acceleration, and I find out that the net force is 6,310 newtons. Now that just tells me that the traction force is 6,310 newtons larger than this friction drag force. In order to find out specifically how large the traction force was, I need to know how strong this drag friction force is. Since they didn't give me that, all I can do is say that the net force in the horizontal dimension is 6,310 newtons. Well, that wraps up what we needed to learn. So let's summarize what we learned. We learned how to predict an object's motion from its forces and vice versa. We learned that Newton's second law relates the three force quantities to each other, the three kinematic equations relate the 5 motion quantities to each other, and the connecting bridge between forces and motion is the acceleration. There's 2 types of problems, and we learned a strategy for solving each type of problem. The first one is forces cause motion, where we're given the force information and need to calculate a motion quantity. And the second type is predicting forces from motion. That's where we're given the motion quantities and we need to predict or calculate a force. Finally, right after this last slide, there's an appendix which is just a review of how to use the kinematic equations from an earlier unit. So if you're a little unsure on how to use the 3 kinematic equations, you may want to listen to this section. Well, this wraps up our podcast. I hope you found it helpful and have a good day. Here's a review of how to use the kinematic equations. I've gone ahead and put our 4 kinematic equations up here just so we have them in front of us. Let's look at a strategy for using them. There are 5 quantities that describe motion: displacement, elapsed time, initial velocity, final velocity, and acceleration. Each equation up above has 4 of these quantities. For instance, equation 1 has final velocity, initial velocity, elapsed time, and acceleration. It does not have displacement. Equation 2 has 4 of the 5. The one it's missing is the final velocity. Equation 3 has 4 of the 5. The one it's missing is elapsed time. And equation 4 has 4 of the 5. The one it's missing is acceleration. We need 3 of the 4 quantities in order to calculate the 4th quantity. So here's our step-by-step process. First, read the word problem. Second, list the quantity you need to find. In other words, that's the answer they're looking for. 3, list the quantities you're given in the word problem. So in the word problem, you're going to be given at least 3 of these quantities and then asked to find a 4th one. So once you have your list of what you need to find and what you already know, you need to pick the equation with the quantities you're given, the ones you know, and it also needs to have the one you need to find. Step 5, if necessary, you need to rearrange the equation to solve for the quantity you need to find. For instance, you may be asked to find acceleration and you're given the final velocity, the elapsed time, and the initial velocity. Well, if that's the case, you're going to need to use equation number 1. Notice, though, that equation 1 is set up to solve for final velocity, so you're going to need to rearrange this equation to solve for acceleration. If you forget how to do that, go ahead and watch the podcast on rearranging equations. The 6th and final step then is to solve the equation. This ends our review of how to use the kinematic equations. I hope you found it helpful and have a good day.